Okay, so first, I'm going to explain how to read and understand the proton NMR spectrum of 2-propanol. So I just went ahead and you can either look it up if you're given the name, or just devise the structure with knowledge of structure synthesis based on the name. So we know that um, propyl is 3 carbons, and then the ol at the end is indicative of an alcohol. So, and then we want the alcohol on the second carbon, so 1, 2, 3, and then we just have to remember that there is going to be this other hydrogen just to give that center carbon a full octet. So now I wrote a couple of notes on the proton NMR of 2-propanol, but the first thing to really look at is how many signals are there. And so the signals are just indicating like the different the different hydrogen environments. And so this over here is one, where I drew the little purple line, and then this over here is another. So there are some other things that we need to look at. So we see that we have on this first signal, so there are 2 peaks, so that means that, and then there's a 6H. So the 6 means that this signal that is accounting for 6 different hydrogens. So, but we have 2 peaks. So that tells us that we probably have methyl groups that are kind of in similar environments, but are a little bit different. So, like, the one methyl group is obviously a little bit more downfield than the other one. So this one that I'm gonna highlight more to the left, that's probably a methyl group that is a little more electronegative based on its surrounding atoms. So we can also look at this 6H. So it means there are 6 hydrogens, and then since we have 2 peaks, we can do 2 minus 1 equals 1 to determine that there is one neighbor that these 6 hydrogens all have in common. So, and 6H, that 6 is the integration number, and just because it's 6, we can kind of be like, okay, so it's probably, just based on the structure, going to be that integration of 2 methyl groups. So 3 plus 3 is going to be 6 here. And we can kind of confirm that just since we know the structure. So there are 3 carbons right here. 3 hydrogens right here attached to that carbon. And then the same thing over here. And we said, based on the number of peaks, that there's one number. So there's that initial peak right here. And then there's that additional peak for the neighbor. I'll do that in a different color. So that additional peak for the neighbor is probably indicating this hydrogen. So if we want to check that, we do have another signal. So the way that I would check that is I would go down here and I'd be like, okay, so the integration number tells us that there is one hydrogen, and then there is this multiplet here, and it looks like there are 7 peaks, so we can do 7 minus 1 to get 6, so we know that it's a signal for one hydrogen and then 6 neighbors, right? And that honestly kind of matches perfectly just based on how we know the structure. And another thing is that this signal is a lot more downfield, and so we know that we do have an alcohol group in this molecule, so this is probably indicating that hydrogen that is attached to that carbon that also attaches to that alcohol on that second carbon. So we know that there are two signals, and then just to confirm that we have 7 hydrogens, and this is not including that alcohol group, so we can take those two integration numbers, and so we can do 6 plus 1 is 7 hydrogens total, and we can go back up here and be like, okay, we have 3 hydrogens here, 3 hydrogens here, that's our 6, and then this is our 1, and there's 7 total. So now, just to kind of understand the orientation of where these hydrogens fall on this NMR, we can go and look at our kind of HNMR, proton NMR spectral information. So I've kind of highlighted where we see this first peak. So we see this first peak kind of between 1 and 2, maybe a little bit closer to 1 ppm on that chemical shift. So that's really going to indicate that we have an alkane, and obviously since we know the structure in this case, we can confirm that. So just having, so we have our OH group, and we have a carbon, and then we have our methyl groups. That is indicating an alkane connectivity, just because we don't see any double bonds or anything. And right here, these methyl groups are the farthest away from the alcohol group attached to that second carbon, so they're not going to have as much of those effects from the electronegativity of the alcohol group. So moving on, we do see that we have between 3 and 4 that multiplet, indicating that center hydrogen on that second carbon. So I highlighted here between 3 and 4, and we see that is indicating that alcohol group. So we see that we have our carbon, our methyls. Oopsies, sorry. And we have that our carbon and OH, and that's really what this is showing us. So this is very helpful in kind of determining, okay, where do the hydrogens fall on the NMR, what's their chemical shift, and what does that mean? And I think so. I went ahead and I wrote some notes on this, but I will go over them. The next molecule, proton NMR, that I'm going to explain is that for ibuprofen. So I just went ahead and I looked up the structure and the formula for ibuprofen, but I will explain how to determine what the proton signals in the NMR mean, kind of in a way that helps if you were not aware of what the structure was, or really like how to piece it all together. So I drew the implicit hydrogens that we're going to see in the NMR in pink, and then I highlighted in green that carboxylic acid that we'll see in there as well. And then I went ahead and I Googled the formula for ibuprofen, and it is C13H18O2. So then I kind of used that to help me determine the integration numbers of each signal. as well as look at some notes and other knowledge of ibuprofen. So the first signal is going to have an integration number of 6, and in parentheses is a D, so it's a doublet. So we know that this signal is going to account for 6 hydrogens with 1 neighbor, because we have a doublet. That's 2 signals minus 1, so minus the kind of like implicit signal, and then we have 1 signal for the neighbor. Moving on to the next signal, we have 3 H, so we have a integration number of 3, and it's a doublet as well, so we'll have 3 hydrogens and 1 neighbor again. And then here we have a multiplet, so we're not really going to worry about that too much, but we just know that we have 1 hydrogen that's going to be surrounded by many neighbors, so we can determine that in a little bit. The next one we have is going to have a integration number of 2, and it's a doublet as well, so we're going to have 2 hydrogens accounted for and 1 neighbor. And then here we have a quartet, and so it's going to be 1 hydrogen with 3 neighbors, because 4 minus 1 is 3. And then here we have a right here we have a doublet of doublets, so that is due to spin-spin coupling, and it's kind of just the overlap of signals that are in similar environments. I'll kind of explain some of the other notes in a little bit, but we just know that there are 2 hydrogens accounted for each signal. And then if we kind of look, we have a doublet here and a doublet here. That's how we know it's a doublet of doublets, and we just know that each of the signals are going to have 1 neighbor, so each of these 2 hydrogens are going to have 1 neighbor. And lastly, we have a singlet at the very end, sorry about that, and it's just going to be 1 hydrogen accounted for, and it's a singlet, so it doesn't have any neighbors, so we do 1 minus 1 equals 0, and there are 0 neighbors. So yeah, and then if we do add up all these integration numbers, we add up 6 plus 3 plus 1 plus 2 plus 1 plus 2 plus 2 plus 1. We're going to get 18 for how many hydrogens are in this molecule, so in ibuprofen. And if we just wanted to account for the number of signals, I think I already said, maybe I didn't. There are 8, so every time you see an integration number, that's 1 signal. So you have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 signals. All right. So I think in this case it is helpful to look at the structure and kind of figure this out. So we know that there is a benzene in ibuprofen, and it appears to be paracyclic because it has, the hydrogens here, kind of even on both sides, and then it has kind of 2 different components to it. So looking at our kind of cheat sheet or chemical shift properties, we can see that between 7 and 8, between 7 and 8, the chemical shifts are typically for aromatic compounds. And so going back, we see between 7 and 8, we do have a doublet of doublets, and that is going to be characteristic of that, or I wrote paracyclic, but that paracentric benzene that we see here. And if we kind of look back at the structure, I'll erase some of this so it doesn't look so messy. we see that we do have all the information that we need to kind of distinguish that. So, and I guess also in terms of like the environment, it is kind of right in the middle there. So it's not super downfield, and so it's not extremely electronegative, but it is it's kind of right there in the middle. So we see that there are, two hydrogens given by that signal, and each of them has, one neighbor. So that is, this signal is indicating that paracentric benzene that gives that doublet of doublets, because if you think about it, these are in a very, very similar environment to, I'll change the color, to these hydrogens over here. So their so spin-spin coupling is going to occur, and their signals are likely going to overlap, which is why we have that doublet of doublets. Another signal that's going to be very, very characteristic is this signal at the very end at kind of between 10 and 12 and at 11 ppm. We see that singlet, and so there's going to be one hydrogen in that case, and there aren't going to be any neighbors. So if we go to our chemical shift information, we see that right at 11, it's characteristic of a carboxylic acid. So we have that double bonded oxygen and carbon, and then we have another oxygen and hydrogen, and if we go up to our structure, we have that as well, and this hydrogen does not have any neighbors. It's just kind of by itself, and this is very, very electronegative, which is why it's so downfield. So we determined those, and I'm just going to erase this to make things a little bit easier to look at. Alright, so we did those. We did that paracentric benzene and the carboxylic acid, which are super major components in ibuprofen, and now we can go back to kind of the more upfield signals. So so here we can kind of piece things apart. So starting at this signal right here, just because we know the structure in this case, we know that there's going to be one hydrogen and three neighbors. So kind of looking at our structure, where do we see that occur? And it's not super downfield. It's not super upfield, but it aside from that paracentric benzene, it is the most downfield signal. So that is going to have the most electronegative effects, likely from that carboxylic acid that we see at 11 ppm. So we just want to keep that in mind, and we do kind of, and another thing I want to say is, while the paracentric benzene is not, it's kind of right in the middle there, it is more electronegative, just because that paracentric benzene does have those carbon double bonds, which does create more electronegativity. Just wanted to clarify that in case you're confused about why that shows up where it does in comparison to this quartet. So I would kind of immediately jump and be like, okay, where is the most electronegative area on this compound, kind of leaving out that paracentric benzene. So we can jump up here, and I drew these implicit hydrogens to make it a little bit easier. And be like, okay, so here we do have 3 hydrogens from that methyl, and then we have another hydrogen, and I think this is a match, because there is this one hydrogen right here, and then it has 3 neighbors. So that's honestly kind of perfect. But if you weren't, aware of the compound and like the structure, and you weren't able to look it up, you could go to this to help. So this is kind of just right between, well, it's pretty close to 4. So, you know, we'll be up here. And I think this is a little bit more difficult because there are no, you know, ethers and esters and things like that, but we are kind of almost in that range of like the carbonyl compounds. So we do have that, or I guess here I'll take a minute to look at it, so I can copy it over there as well. So if we see, we do have kind of following this, we do have that oxygen double bonded to that carbon, and then another carbon, and then that other hydrogen. So I think that does fit very well. And while this does show up a little bit, I think closer to 4 than where we would want to see this for the carbonyl compounds, I think it's still really close because, you know, looking at the structure that, you know, you don't have an ether, an ester, and we don't really have alcohols or there either because it's just from that carboxylic acid. So that is a way to determine it and kind of work your way through it when you're given the proton NMR, because you know that, you know, it is 1 hydrogen and 3 neighbors, and that's kind of the only place that really occurs, and that is more electronegative. So then moving backwards, we have this 2 hydrogen situation with 1 neighbor. So oh, and there's one other one that I actually ended up leaving out, I believe. Oh, we have another hydrogen right here. Alright, anyways, moving on. So back to this. So this is so now we did that other side with that carboxylic, so we did that top end with that carboxylic acid and the quartet. So now I think we know that there's that paracentric benzene there, so we can kind of just focus like on this region right here. I will put a little, I guess I'm gonna put a little box around it. So, oops. So we know that we have 2 hydrogens in the signal, and there's going to be 1 neighbor. So if we look over here, we can see, okay, where do we have 2 hydrogens and 1 neighbor? So these methyl groups wouldn't really work because there are 3 hydrogens, and they're kind of in a similar environment, so we'd likely have a different integration number for that. So I think the match would really be this, these 2 hydrogens with this 1 neighbor. And, you know, if you're given the structure and the implicit hydrogens aren't drawn out, I think it's very helpful to draw them out because, you know, just because they don't show up in the structure, they are going to be in that proton NMR. So anyways, moving back, we determined that one. Alright, and then we have this multiplet right here. And we can be like, okay, so we have 1 hydrogen and it has just, you know, so many neighbors. So I think it's really going to be characteristic of this carbon right here, this hydrogen right here, this implicit hydrogen that I did not draw out, and it's because we have those 2 hydrogens to the to the right, and then those 2 methyl groups to the right, and so together that seems to be, yeah, that's 8 neighbors, so that is a multiplet. So moving back here, so I guess I kind of skipped over this one, but this this one, this 3 hydrogens in one neighbor goes very hand in hand, or I guess I'll do it in the same color, goes very hand in hand with that signal from the quartet. So right here we have, there are 3 hydrogens, and then that one neighbor right here. So that one is also taken care of. And then moving on to that last one, we have 6 hydrogens with one neighbor, and I mean, our really only option left is these 2 methyl groups. So we have that 3 plus 3, so each methyl group has 3 hydrogens equals 6, so that matches with the integration number. And then right off of that carbon, because these 2 are in that same environment, they do have that one singular neighbor. So that implicit hydrogen that was not originally drawn out. So yeah, that is kind of how to work through the NMR. I think the structure is a little bit more confusing because there is a lot to think about in terms of, I can erase all this, in terms of what's downfield and what's upfield and what's more electronegative and what's, is there spin-spin, coupling, how do I draw this out, but I think the really, really important portions of this to notice are the carboxylic right here, and then that paracentric benzene, because then you just kind of have to work through it, and where does everything fall. And so just to go over that electronegativity again, this side is going to be less electronegative, so it's kind of less exciting, and this end is going to be more electronegative. I think it does get a little bit complicated when you have so much over here, but you can also consult, a table such as this one, and just some more spectral information, like this is going to be more indicative of alkenes over here, which we can also kind of compare to our, our methyl groups, and, alkanes, to our methyl groups, and then, you kind of also have to remember if something is closer to that paracentric benzene, it is going to be a little more downfield, which is why we see this, indicating this 2H1 more downfield than this methyl group per se, and why we see this hydrogen, more downfield than that one of the multiplet, because it's closer to this, carbon-carbon double bond, so it will experience more of that electronegativity. So yeah, those are just some things to think about, and I hope that this was helpful.